Next thing I'm going to do is open the analysis file that I shared with you. And this will provide some examples of stuff that I would want to do to analyze the data from this real study that me and Rosanna conducted. This just explains that. I might want to get some well, first, I might want to attach data.ok. This is, again, not always necessary. In this case, I thought it would make some of the code more compact if I could just refer to the names of variables in data.ok directly without having to specify that that's the data frame I'm intending to work with. And let's just get some background information about the main variables we're interested in. So the first thing I'm doing here is just looking at how many people are in each condition. 125 in the illegal condition, 126 in the legal condition. Seems fine. I don't have any particular reason to need to know that information at this point, except that I like to have a feel for what my key variables look like before I use them in analysis. I might also be interested in this you ever depression variable, which I have a quotation from the survey here. The exact question text was, have you ever experienced any kind of depression? The answer here is that 125 people said yes. I don't remember it being that many. No, it's right. That's in the raw data. Okay. I guess maybe it shouldn't come as such a surprise because depression is quite a common experience. But yeah, we have a lot of people responding yes to that question. And so maybe I will consider thinking about them in my analysis. I'm not going to exclude them from the analysis. There's enough of them that instead I could actually compare them to the people who answered no to that question. Next, I will look at a tabulation of these two variables together, condition and whether the participant reported having experienced some kind of depression, just to illustrate what table does when you supply two different variables as arguments. It will provide you with a two-dimensional table. And you can also do a chi-squared test based on that two-dimensional table by calling the chi-squared test function, which in this case, there's a few ways you can call this function, but one way is by supplying two variables that the names of two vectors, which represent variables, that they could create a two-dimensional contingency table. And here is information about that chi-squared test. It applied Yates's continuity correction automatically, which is perfectly fine and appropriate, but you should keep that in mind if you're ever wondering about if you've learned the formula for a chi-squared test and you're wondering why the result is not exactly the same as what your formula would tell you. So not statistically significant, which should not come as a huge surprise because based on this distribution of responses, it doesn't seem like participants reporting that they ever had depression was really responding to the experimental manipulation. And I wouldn't necessarily expect it to, but if I'm going to analyze this report of having ever had depression, it would be really important to know whether it responded to the experimental manipulation. I can also do this Fisher test. This is Fisher's exact test on the same variables. It tests the same null hypothesis as the chi-squared test, but it's an exact version of the test rather than an approximation of it. But it does not provide strong evidence that the response to the question, have you ever had any kind of depression, varied depending on the experimental condition. The next thing I'm going to show you is this describe function from the psych package. Yeah, this is what I was remembering. Scale. The function I mentioned earlier, scale, that is in base, but I thought was in psych. And this describe function is in psych, is that I use my own versions of both of those variables most of the time, both of those functions most of the time, and so I forget sometimes where the originals come from. But here I'm just creating a small data frame with some of my variables in it and running describe on that data frame to illustrate what this function can do. It's pretty handy. It gives me information about each of these 6 variables, all kinds of details. the mean and standard deviation may be particularly important to some people. So a good reminder that this evaluation of Amy is on a much wider response scale than most of these other variables. The mean is around 70. It ranges from 15 to 100. Nobody used the very bottom of the scale. Not a huge surprise. People generally shy away from really saying that they hate a hypothetical person in a story that they just ran, unless that person did some kind of horrible deed. I might spend some more time pondering that if I was actually analyzing this data set for the first time. I'm going to show you some quick plots. So this question, discrim is legal, is kind of like a manipulation check. It just asks participants whether they think the form of discrimination described in the story is actually legal or not. The judge in the story told them whether it was legal or not, but of course they might not believe the judge or agree with them. So here's a histogram of that information. This basic histogram has some handy defaults. It works okay. But for a variable that has relatively few unique values that I don't necessarily want to bin them, I want to plot every unique value, I can also do this, plot of table of that variable. And I get something like this, which is quite handy. So this is like a histogram, but here I know that each of these bars represents a unique value. So they're not bins anymore. And so I can, definitively say that a bunch more people responded with 7 than 6.5. Anyway, a bunch of people were unsure whether discrimination is legal, or at least responded at the midpoint of the scale. It doesn't mean they're unsure. Maybe they think it's sometimes legal and sometimes not. And let's suppose I wanted to illustrate more clearly why the histogram function and the plot function called on the output of the table function are different. Well, I might like to plot both of those things right on top of each other or next to each other. So this illustrates how to do that. The par function sets graphics parameters, and it can, in this case, set up a plotting space with certain properties before I actually make any plots. This just tells it that I want to set up a plotting space with room for 2 plots in it, and they'll be entered by rows. So here is that space. It's empty right now. And then I can call these 2 plots, the histogram and the plot of the table of discrimination is legal, and they'll show up next to each other. I'm going to stretch this out so we can take a closer look in a second, but real quick, this argument to the par function specified that I wanted the resulting space to have 1 row and 2 columns. That's what this 1 and 2 mean in this vector that's applied as the argument to MF row. And that's what happened here, right? This space can be thought of as a grid where on the left we have 1 cell and on the right we have another cell, and those can be filled in with plots. I'm pretty sure there is a discrepancy here. I just have to find it. Yep, there it is. Okay, so it's that 1 and 1.5 got lumped into the same bar for the histogram, but not for this tabulation, right? So you can see that around 55 people responded with 1, and another 9 responded with 1.5. This is an average of 2 questions. That's why half values are present. And here we have all 64, or however many exactly it comes to, in this bottom bin. And so this version shown on the right, oh, I'm sorry, I was pointing with my mouse. You can't see my mouse. I was looking at the left 2 bars in each of these plots. The point is that the one on the right, the plot on the right, is a little bit more precise. Par is really useful for all sorts of things besides just setting up plotting spaces ahead of time. And so this is probably the most common help or documentation page I look at. I'm typing $par in R several times a session when I'm using R, probably, at least if I'm graphing in base R, because it has all kinds of stuff that I often forget the exact names of some of these arguments. And these can be used not just in the par function, but often in specific plot functions. So just one quick example. If I wanted to know, even if I didn't feel like scrolling through and reading the whole thing, let's say I wanted to know how to set up the margins. I know that's mentioned on this page somewhere, so I'm just going to type margin. That's not the one I want. This one's pretty good. MAI is one of the margin arguments, and this helps to describe what I can do with that argument. MAR is another one, and this helps me describe what I can do with that argument. Um, so I encourage you, if you're going to play around with plotting in base R, to read this page once through, one time in your life maybe, and come back to it frequently. Don't expect yourself to remember what's in it, but just remember the kinds of things that are in it so that when you need to find something, you'll know where to find it. I will show you some more sophisticated examples of plotting in base R next week. Oh, so I walked through comparing those plots, but here's an even easier way to compare them. I'm going to use MF row equals the concatenation of 2 and 1 this time, 2 rows in one column, and here are those two plots, one above the other. Now you can much more easily see, I think, that these leftmost two bars are different because in the top plot, 1 and 1.5 are getting grouped into the same bin. A few more examples of plots. So I might call plot of table of the question most people support discrimination on the basis of mental illness history. So here is that plot, reasonably symmetric distribution. I could try it with this composite scale indicating that the participant supports discrimination, which I called I support discrim, just as a way of reminding me how it's different from most support discrim. But here, now suddenly this is starting to become very difficult to read. So this is the point where this variable was the average of too many component parts. It has too many unique values, and I would not like to see them each plotted individually like this anymore. So instead, I'm going to use the regular histogram function, and I get these nice bins that work really well if the variable is more numeric and less categorical. I can also look at a histogram of the evaluation of Amy. This has a 101 point scale, and of course it's left skewed, like I described before. Most people tend to avoid using the bottom portion of this scale. Here is the composite evaluation measure based on z-scores, also left skewed. And here is the trust quartz variable, just as different examples of variables that I'm going to be interested in looking at later.